In this video, we are going to talk about MSC Nastran Solution 400 results, and we're going to go over a very simple example. And this example is Chapter 5, Steel Roller on Rubber, from the MSC Nastran Implicit Nonlinear Manual. So if we look at this problem, this is what we have. This roller is going to rotate and move this rubber base. So some of the pieces of information that we want to look at the motion of this roller on the rubber base. And then we want to look at some time histories. So one of the primary time histories we're going to be looking at is the force on the steel roller. So here, let's go ahead and scroll down through chapter 5. And so this is one of the plots we want to replicate. Here you can see what the force is on the roller during the 2 seconds of the motion. And then here is a snapshot of what the steel roller looks like during the motion. So let's go ahead and get started. Let me close some of these windows, or actually I'll leave them open. So before going any further, let me point out the tools that we're going to be using today. So today we are going to be using the post-processor web app that you see on the screen, and we are going to be using the HDF5 Explorer to make our graphs. And let me go ahead and bring up these 2 bullet points. The post-processor web app is free for all MSC Nastran users. Whether you're a student, professional engineer, or researcher, the post-processor web app is free for you to use. Also, the post-processor web app is only compatible with MSC Nastran. This tool is not compatible with any other versions of Nastran. For those who want to start using the post-processor web app and the HDF5 Explorer, you can visit theengineeringlab.com. Here at the top right hand corner, you'll find a blue button. Click on the blue button, fill out the form, and we'll get you started with either an installer to install the web app, or you'll get online access to the web app. So let's go ahead and get started. So I typically like to start with the empty downloads directory. The reason is because I don't want to get confused when I'm working with other files. And here we'll go ahead and click the tutorials link to open the user's guide and the tutorials section. Let's go ahead and click on post-processor tutorials. Scroll down until you find this example. MSC Nastran SOL 400 results, displacement forces of a steel roller moving on rubber. Let's go ahead and click that. And let's go ahead and extract the contents of this file. Now, we only have a bulk data file for this example. Here we have all the nodes and materials, the elements, the loads, and boundary condition. This is already ready to perform the analysis. So that's what we'll go ahead and do. We'll go ahead and start Nastran to perform the analysis and produce the results. While this is happening, I'll go back to the home page of the web app and I'll click Viewer. And here I can go ahead and upload that bulk data file. So let's go ahead and do that. And let me zoom out a little here, maybe change the background color. And so this is our model. One quick comment about this model. This is the version that's dealing or working with 2D elements. Now, the reason I did not go forward with the 3D element version is because the 3D element version is going to take many minutes to solve. But this 2D version should run pretty quickly. So that's why I chose the 2D version instead of the 3D element version. If you wanted to, the documentation also has a version for the 3D element version. So if you go to the end of the chapter, this is where you'll find various versions of this example. So here today we're using example B, which would be this example. If you want to replicate this with the 3D elements, you could use either this file or the file underneath it. So again, today we're using the 2D element version. And right now what I'm going to do is I'm just going to pause the recording here because the analysis is still running. So we'll go ahead and pause it and wait a few moments until this is done. So Nastran has just finished the analysis. So what we're going to do now, let's go ahead and open this in the HDF5 Explorer. So what we're going to do is, or before we get to the HDF5 Explorer, we're going to upload the H5 file. The H5 file is going to contain the results of this nonlinear analysis. So let's go ahead and click upload here. Now, after you do this, let's go ahead and give this a few moments to open the post-processor web app. So now we're in the post-processor web app. Let's go ahead and select time step of 0.5 seconds. Now, when you do this, the scale factor of the deformation is 10, which is not what we want. So let's go ahead and set the scale factor to 10. And so this is what the motion looks like. Let's go ahead and maybe go back to time step 0.1 seconds. So here, if you look at this column, the time column has time in seconds. So here's 0.1 seconds. Here is 0.5 seconds. And here is 1 second. Now, what I can do here, let's go ahead and jump here. Let me open the HDF5 Explorer. And let me open that same H5 file. And let me do some interrogation here of the model. If we look at the very bottom element, let's go ahead and pick that element and display the nodes or grids for that element. So if we look here, the very bottom node is node or grid 211. So what we're going to do here in the HDF5 Explorer, we're going to go ahead and find the displacement dataset, and we're going to type in that node ID. And then we're going to click acquire dataset, and then we're going to create a plot. So here at the top right, there's a button called create plot. Click that button. This link at the top, last plot added, starts to blink. Click that link. And now it shows you the displacement of that node for the bottom. So this is what we want to know. What is happening with this node during the 2 seconds of this analysis? So let's go ahead and display maybe the Y component of deflection. And if we go back to chapter 5 and read the problem statement, here we get some information about what's going on for the first second. Here it says that the roller is not rotating. The only thing that's done is that the bottom surface of the rubber is moved upward by 3 millimeters. So if we go back to the viewer, so we are told that this bottom surface is moved upwards by 3 millimeters in the first second. So what we're doing is we're taking node 211 and we're creating a time history of the motion along the Y component. So here for the vertical axis, I selected the Y component. And if you look at what's happening in node or grid 211, you see that the node is actually being moved upward by 3 millimeters. And then for the rest of the analysis, the bottom of the rubber base is kept at 3 millimeters. So that's one of the plots I wanted to show you. Now let's go ahead and see what else we can do here. Let's go ahead and create some snapshots of the motion of the rubber base and the roller. So let's go ahead and go back here. Let's go ahead and jump into the post-processor web app. And sometimes it helps to zoom out a little. Sometimes the interface gets really big. You can't really see what's going on. So let's go ahead and zoom out. And what I'm going to do now is go to maybe 0.5 seconds. No. Let's go to 1.5 seconds. So let's go ahead and mark this checkbox. So this is what the roller looks like after 1.5 seconds. Now, I should mention that the roller is not being translated. Only the rubber base is being translated. The only thing the roller is doing, it's rotating. So let's go ahead and jump through some of the time steps. So here you can see what the roller looks like when it's rotating. Now let's go ahead and go to the very end. So here you can see that this is what the end of the motion looks like. And so that's how you create these different snapshots for the motion of the roller and the rubber base. Now there's one last graph that, or there are actually a few last graphs that I want to look at. in this example, they have a question for us to answer. They want to know, let me scroll up to the problem statement. They want to know how much point A has moved during the analysis. And you might be asking, okay, what does point A look like? So let me zoom into this diagram here. Point A is going to be this point on the rubber base. So let's go ahead and jump back to the web app and let's go ahead and click on Fem label. Let's go ahead and zoom in a little. Let's go ahead and reset all labels. Let's go ahead and click on enter pick mode. We'll pick this element here. And then we want this node ID, which is node 421. So let's go ahead and go back to the HDF5 Explorer. And we'll go ahead and type in 421, which is this node or grid. And we'll click acquire. And then once we have all the displacements for that node for all time steps, we'll go ahead and click create plot. Here at the top, click on last plot added. And let's go ahead and look at the X component of motion for that node. So here for the first second, there's no lateral or horizontal motion of the rubber base. Remember, for the first 3 seconds, we're only moving up the rubber base by 3 millimeters. Only after the first second do we start to rotate the roller. So at the very end, we get a final displacement of negative 175.7761. So let's go ahead and write that down. Or what I can do is this. I can actually go here and just copy that value. So let's go ahead and copy it. And so that's the answer to that question that we were asked a moment ago. When they said this part, they wanted to know the horizontal displacement of point A after 360 degrees of rotation of the roller. The answer is this, negative 175.776. And if we go back to this document, and if we scroll down a little, for the case when you use 2D elements, this is what we are expected to get. So this would be the 2D segment to segment contact scenario. And you can see that we get 175.776, which is the same value we just saw in the HDF5 Explorer. If we were to use the version with 3D elements, we would have this value, 182.903 millimeters. Okay then, so let's go ahead and see what else do we get here. We want to look at the vertical force on the steel roller. So how do we get this plot? So since we moved the rubber base vertically upward 3 millimeters and then we rotated the roller, we want to know what the load on the roller is during this 2 seconds. So if we go back to the HDF5 Explorer, let's go ahead and select this data set, contact global, and we'll tap in contact body ID 1. This roller has a contact body ID of 1. So after we do that, we'll go ahead and click acquire data set, and then we'll click on create plot. And once you do this, click on the last plot added. And here we want to look at the force along the Y direction. And so this is what we get. You can see that the force during the first 1 second is somewhat linear. Remember, we're only moving the rubber base vertically upward. And then here you can see that the force on the roller varies a lot. And this is because as you rotate the roller and because of friction, you have the force vary a lot during this analysis. So that's how you create this plot here. You'll notice that in this plot, they've actually taken the absolute value of this data. So what you could do if you really wanted to, here is a table of the same data that's in this graph or plot. You can click download CSV, and then here you get a CSV file. So if you really wanted to, you could take maybe the absolute value. So let's go ahead and maybe try this. Oh, it's not right. Let's go ahead and do this. So let's go ahead and just do that here. And we'll do that here also. And we'll go ahead and select all time steps up to 2 seconds. And let's go ahead and give this a row for the time steps. So we'll go ahead and put this here. So this is going to be time step, and then here a vertical force, which is in newtons. So let's go ahead and type this, and then we'll go ahead and select these 2 rows and create our graph. Let's go ahead and see which one works well. So it would be maybe this one. So here's the same graph, this time with the absolute value. So here it goes up to maybe about 250 newtons, and then you can see the force varies during the next 1 second up to 2 seconds. So there you have it. That's how you look at results for MSC Nastran SOL 400 with the post-processor web app and the HDF5 Explorer. Both of these tools are free as long as you are an MSC Nastran user. So if you want access to both of these tools for free, all you have to do is go to theengineeringlab.com. Here at the top right, click this button, free download post-processor web app, fill out the form, and we'll get you started with either the installer to download and install the web app, or we'll give you online access to use all of these tools. So with that, I'll go ahead and pause it there. And as always, thank you so much for watching.